So the field will be normal. So this will be my E field at the boundary, right? This is my E1. It's a vector, okay?
Fuck.
And E1 is the same as the, remember the, um, between conductor, perfect conductor and this was the normal component simply what? D normal have equal to the charge density, right? So at this interface, so if I blow this up at this interface over here, so if I just draw the interface, so this, imagine this very, very thin conductor. Over here you have the E field, E1, and here of course we'll have some kind of surface charge, which is rho s, right? So we know that E1, the magnitude normal, we know already normal is equal to uh, rho of s, this epsilon, so rho of s over epsilon, whatever epsilon 1, right? Does it make sense? That's the boundary conditions, okay? So now I know that in this region, I call this region we have E of 1. So the E of 1 will go from here to here. This is my E of 1. In the second region, I have E2. And in the third region, I have E3, right? So at this boundary, I have this E1 equal to whatever charge density that I have over here. So in other words, if I try to use this. So whatever I have, this is the charge density, right? Okay, so now in medium one, the first boundary, so this is the first boundary condition. Oops, let me do this. This is the first boundary condition. Then we have second boundary condition, and I have third boundary conditions, and I have the last fourth boundary condition, right? So I have how many possible boundary conditions? There are four. There are four boundaries, correct? So the first boundary, this is what we have. In the second boundary, what happened at the second boundary? Second boundary, we have this is epsilon 1 here, mu 0, epsilon 2, mu 0, right? And then here on top, we have this is normal components. This is my E1. The bottom part, I have my E2, right? And I know that the normal component has to be the same for the D. So I know that the D, so this, what it means in this boundary is that at this boundary, epsilon 1 E1 is the magnitude, because I know it is already normal. I know it's normal component. I don't have to worry about the vector at this point. I understand that this only have normal component. E1, epsilon 1 E1 has to be equal to epsilon 2 E2, right? So that's at the second boundary. At the third boundary, I have a metal. So now this is a bit more complicated. So let me uh, add another page. So at the third boundary, I have conductor. So let me blow up the conductor a little bit, make it a bit bigger, right? So you can see it. So this is the third boundary is where you have E2 over here, right? And then I have E3 at this over here. Well, what happened at this boundary? How do I know? Well, E2, of course, because this conductor is basically floating, and I do not put any charge in it. So if I put a potential, then what happens is that some of the charge will be pulled, right? So the bottom, because I have over here, I have the negative. Remember over here, oops, let me redraw this. Let me just erase this one. So I have it's E over here. And then here I have another conductor, right? So I kind of blow up a little bit, make it larger so you can see, assuming it's very thin. So over here, I know these are negative charges right here because I connect to a negative voltage, right? Remember this, I connect to a negative voltage here. So this connect to the positive voltage up there. So this, I have the negative charges over here, right? So negative charges, then at the boundary condition, the field will be pointing inward, normal, correct? Now, for this particular conductor, what happened? If I put negative charge here, because this is not neutral, it'll pull the positive charge on this particular conductor, right? And the same amount will be, if you pull the positive down here, then the same amount will be appearing on the top. Does it make sense? So the whole thing is still zero. The whole thing for this guy, the whole charge, the Q on this particular conductor is equal to zero. I think do we call it, well, just, yeah, equal to zero over here, Q total, all right? So for this particular conductor, the Q total is zero. This one is not, because we pump it with a negative voltage, right? Any questions? So now, therefore, the E2 will be normal to here. And because it's neutral, we know that E2 has to be equal to, again, related. So the E2 with this, in other words, now E2 normal equal to whatever. Let's call this rho S 3, right? Let's call this rho S3, right? But this is negative, so that's why it's pointing. That's why it's pointing inward, because it's negative. This E2 is pointing toward the conductor. That's equal to rho S3 divided by epsilon 2, right? Any questions? Now, if we look at the bottom part, the E3, again, the direction already taken care of because it's a positive charge. That will be equal to, again, because it's the same charge, so it's still rho S3 divided by E3. Now, this rho S3 and this rho S3, they are the same, right? The amount is the same. They are opposite sign, which we take account for already in terms of the direction of the E. Therefore, what does it say? In this case, what it tells us is that epsilon 2 E2 equal to epsilon 3 E3. Any questions? Anybody have any question at all? Yeah. What if you want to say something, you just unmute yourself and then you can say something. All right. The system automatically pick you up. Any questions so far? So now I have how many? So what's the fourth one? The fourth boundary condition is easy, same. So the fourth boundary condition is we have. Oops, let me clean this up. The fourth boundary condition I have, again, a conductor here, right? So because it's negatively charged, so it is the field will be going in this E3 at this boundary condition. At this boundary, it's normal to the surface. And what is E3? Well, E3 is simply equal to whatever charge that we had earlier, rho S over epsilon 3. Okay. So now we have described the boundary condition. Here's the first one, which I call the top one rho S. The second one is like this, just simple boundary conditions. The third one, I account for this like this. So you can see this is the result, epsilon 2 E2 equal to epsilon 3 E3. And then finally, I have this rho S, right? Any questions? Yes.
Could you go back to the previous page for 1 second?
Okay.
Thank you.
So I'm not using anything else. I just make use of the boundary condition that we learned in class. So all of these we solve using boundary conditions. Any questions? I don't have to memorize any formula. I just know the boundary conditions. So I know how the electric field in each region compare, or maybe I should do this, huh? Okay. Can you see me with the video as well?
Yes.
Right. So, well, maybe I should switch to a. Okay. Let me play this trick. I don't know if it works. I should be able to do something interesting. I don't want to stop video. I can have. Okay. I can do this. Okay. Now I can. Oops. So you have to flip your computer, huh? That doesn't work. So let me do this. I'm afraid that it may not look as good. So this is you can see me pointing. That's the whole point. It's upside down, or yeah, it's upside down, right? Is it correct like this? Actually it works.
No, that one was upside down. You had it right the other way.
The other way is right?
Yeah.
Yeah, okay. So this is better?
Yes.
Are you sure? Okay. What happened here? Now I'm messing up over here. Okay. So the points that I want to be able to actually show you what I point to. Is it okay? Or can you see that okay or no? Blurred. Okay. So I need to, I don't know, you know how to focus or not. How's it? Good. I thought it was. I see it here. It's upside down. Are you sure? You guys doing okay or really?
Yeah, it's good.
Are you sure it's right or upside down?
Right? Oh, it's good. 100%.
I'm sorry.
It's good.
Okay, one of you speak at a time. This is good. Okay, you can see that, right? So I have these three field E1, E2, E3, right? I thought it's kind of flip left and right. Is that right? No?
It's straight up and down. It's ready to go.
Okay. So you all right. So that's epsilon E1. And so this at boundary 1, boundary 2. So I have all the relationship in each of these boundary, right? I do not do anything fancy. I just use the boundary conditions. All right. So now I have this. Everybody get this down? All right. By the way, this I can save it. I can email to you all later. So okay, all these boundaries. So what I end up with is the following. Let me rewrite everything. Okay. So what I have now is epsilon 1 E1 equal to epsilon 2 E2. Right now, I understand I already take care of all the directions. I take care of the directions. I know where I know it's all of them is going to be normal to the conductor, and then the line is always going away from the positive charge, right, on a boundary conductor, and then in the interface between the conductor and the I'm sorry, between two dielectric, the normal component has to be of the electric flux has to be continuous, right? So I also know that therefore I can express this E2, again the normal component equal to epsilon 1 over epsilon 2 E1, right? Any questions? So I can also do the same thing for at the boundary, the third one, epsilon 2 E2 equal to epsilon 3 E3. Therefore, my E3 is epsilon 2 E2 over epsilon 3, right? So, well, epsilon 2 is related to the epsilon 1, right? Therefore, this E3 equal to epsilon 2 over epsilon 3, and then have epsilon 1 over epsilon 2 E1. So actually, this cancel out. So actually, I have the following relation. E2 equal to epsilon 1 over epsilon 2 E1, and then E3 is equal to epsilon 1 over epsilon 3 E1. So I express everything in terms of E1 now. All right. Any problem? So now I know that in this structure, and then this, right? E1 here, the magnitude, I just do, okay, let me just do the whole thing, E2 and E3. So I know that this E2 related to E1, E3 related to E2. All right, any questions?
Sir, could you scoot up the iPad, please?
Oh, okay. So, right, so you actually you can see on the other screen, you have two screens, right? You can see both, right? All right, so now I also know that here I applied voltage to it, right? What is the voltage? VC. And this is plus side, this is negative side. So I know that, and because the field are uniform, E times the distance here, all of them have a D, right? So I know that E, what's the unit for E? Volt per meter. But if I multiply that, because I assume it's constant in all the region, then E times the D will give me the voltage across each of these boundary, right? So therefore, I know the next thing is that VC is equal to E1 times D plus E2 times D plus E3 times D. Any questions? Now I take care of the arrow or the direction in the drawing, so I don't have to worry about the vector over here. Any question now? Okay, so now they're all the same, right? D is all the same. Therefore, I can pull the D out. So it's basically, now I can express all the E, so basically E1 plus E2 plus E3, right? I still cannot solve it because this is given, you know, the voltage, but we don't know what E1, E2, E3. Well, I know D. So what I can do then is I express everything in terms of E1. So let me use another page. So another page is, everybody got this down? So what I'm going to do is I'm going to express all E2 and E3 in terms of E1, like the field number 1, right? So if I do that, V of C, which is known, equal to D times E1, and then, of course, I have 1 plus epsilon 1 over epsilon 2 plus epsilon 1 over epsilon 3, right? Any questions? Because E2 is epsilon over epsilon 2 times E1, E3 is epsilon 1 over epsilon 3 times E1. All of these are known. These are known. I know what epsilon 1 is. I know epsilon 2 is. I know epsilon 1. I know epsilon 3. Therefore, I can solve for E1, right? Therefore, what is E1? E1 is simply VC divided by this whole thing, right? Divided by D, and then 1 plus epsilon 1 over epsilon 2 plus epsilon 1 over epsilon 3 inverse, right? That's it. So that once I get E1, I can solve for E2, I can solve for E3, I can solve for E4. Any questions? Is that clear? So then I can express, so the question is, what is the E, right? What is the question is, what is the E for different region? So of course, then of course E1, if I do the coordinate system in terms of, if I want to be proper, I have to define a coordinate systems, right? So any question, you can, so if you draw it, then E1, so this is E1. So if so this is my E1, here's my E2, here's my E3. So it depends. If I use a coordinate system like this, if I call this over here is X, over here is Z, I pick a coordinate, I pick this one. Therefore, if I pick this coordinate, so where's X, where's Y, Y is going in, right? X, Y, Z. If I use this coordinate system, then my E1 is equal to negative Z hat, right? E1, correct? My E2, also negative Z hat, E2. But this is between, so now I can say here, this is for Z between E1, Z between, this is 0, D, 2D, 3D, right? Correct? So this is for Z between 2D and 3D, right? Yes? So that's E1. E2 is Z between D and 2D, between this, right? And then E3 equal to negative Z hat E3, where Z is between 0 and D. Any question about this? Is that clear? So the value can, so once you have E1 over here, you can find, so once you have E1, therefore, how do you find E2? Well, E2 is simply this, right? Epsilon over epsilon times E1. And then E3 is simply epsilon over epsilon 3 times E1. So you can solve for the rest. So this is the first part. Any questions? So what have I used to solve this part? To solve for the field inside this layer of capacitor? Very simple. I recognize the relationship between different regions, apply the boundary conditions, and I also know that as the field multiplied with the distance give me a potential. And I know the total potential between the two terminals up here has to be equal to V of C. Therefore, from there, I can solve for my E because they are all the E are related. Once I figure out the one, I can solve for the rest. And the rest is simply I have to specify the geometry so that I can put the vector notation appropriately. Any questions? Any question at all? So that's the first part of the questions. So what's the second part? So this is the one that causes a lot of headache for a lot of you, right? Second part, can you read this or no? Okay, the second part, you're asked to solve for the potentials inside the from between 0 to 3D, right? So what if I ask you, what is the potential? Let me use a different color. So what's a V at this location, right? What's a V? V at given Z, right? What's the potential? Okay, so how do we solve that? Well, we know that V. So this is part A. We already solved for part A, right? So let me use here's part A. So part B, we know that V for any given Z is equal to, so the Z is from 0 and up, right? We start with for Z at 0 at the bottom plate. So the bottom plate is Z equal to 0. The top plate, the Z equal to 3D, right? So yes, someone has a question? All right. So somebody forgot to unmute or anyway, yeah, but if you want to ask questions, just unmute and then ask questions. So V of Z is basically, we are interested only with Z between 0 and 3D. Outside, of course, the potential will be 0. We're not interested in it, right? We're only interested in this. So this is integrating from whatever Z is, from 0 to that value of Z, right? So basically, because we're going against, remember, it's supposed to be negative, but because the way we do is already negative Z, so negative Z cancel out. So we have E dz. Any questions? I already take care of the negative part, right? Technically speaking, it should be, let me do this. Let me, from the formulation, let me clean this up. So let me write down, recall V1 minus V2, right? Equal to integral from first location P1, maybe let's call this P1 to P2, right? Negative of that. E dot with dl, right? Remember that? From 1 to 2 is, sorry, so this then becomes something missing. So this is supposed to be V2 minus V1. You go from here to here, right? So it's V2 minus V1. Is that correct? But it's negative E dot dl, right? Any questions? So it's negative E dot dl is this what we have. So if I want to know the potential between here and here, what I have to do is, well, all of this are negative Z, right? So let me clean this up. This kind of mess up a little bit. Okay. All of this negative Z. So the D of L for us is Z, right? So I'm interested in, so I'm interested, let me redraw this. What we have is this. Now I have, this is my Z. Here's my capacitor. Let me use a different color for the capacitor. So I have here, and then here, and then then here, right? Here's my E1 inside here. Here's my E2. Here's my E3. So my Z is from 0. So this is my X. Here's my Z. This from 0, D, 2D, 3D, right? So I want to do, we want to solve for V of Z, where Z is between 0 and 3D, right? So in this case, what is the D? So we want to integrate over Z. So our integration is, so our DL equal to Z hat dz, right? And our E, on the other hand, is all of our E, so E whatever N is equal to negative Z hat, some En, right? Yes, in all of the region, this is our E. So when we do the dot product, what happened? Becomes negative, right? Negative. So the formula calls for negative. So negative and negative cancel out, right? This negative. This and this cancel out, right? So now the formula becomes, I can look at region by region now. So let's look at region 1, right? So first for region z between 0 and d. So what is the potential? In this case, v of z is equal to, now that I end up with 0 to d, I'm sorry, to whatever point I want, not to d, but to whatever point, to whatever z I want. But this z is between this region, between 0 and d. Okay, so I have in this case, it's E3 dz. Oops, how can I write E2? E3 dz. All right, so we know what E3 is, right? So this E3 dz. Well, it's simply E3 is not a function of space, it's constant. Therefore, I know that we know the value already. So it's nothing but E3 times z. Any questions in this region? Right? So that's straightforward. Second region. Now you have to be very careful. So z is between d and 2d. Right? So you are now wanting to find the potential from here to here. Can you see it? Right, from this to this. So basically, these formulation tell you the potential between P1 and P2, right? Okay. So the total potential will be, so any question up to this point? So in this case, what we have is at V, in this case at Z, is equal to integration from the, so I need to find the potential from here in any region here, correct? So in this case, I have from D, integral from D to 2D, right? To Z. So my Z is between these, right? E 2 dz, but I have to add the potential over here. So plus the potential at D, right? V at D. Does it make sense?
Dr. Tjuata, can you move it
Yes.
up a little bit?
I'm sorry?
Can you move it up a little bit, please?
Oh, okay. So here, in other words, but remember, the formulation is for potential from this point to whatever point, right? So when I solve that, I have to add this potential at this point. The potential at this point is this guy. Does it make sense? Is that clear? Or technically speaking, the potential at any point, the reference right here. Here's our reference, right? The reference is 0, right? Our reference. So you have to integrate from the reference to whatever point. Okay. Now, if z between these two, then I can do the following. So let me, maybe, any question here? Maybe let me do it one more time. Maybe let me do one more steps. So basically, let me erase this one. So basically, let me redo this part. So z between d and d 2d, then the integration, actually the reference is at 0, right? Our reference point is 0. So I integrate from 0 to d E3 dz, right? Plus integral from d to z E2 dz. I get rid of all the negative sign because the dot product is already taken care of. Does it make sense? So what is this? This is nothing but E3 times d plus E2 times what? Z minus d, right? Any questions? So if z between d and 2d, this is the potential. Everybody see that? Any question at all? All right. Because our reference, remember our reference for our voltage is at 0.0. So now, how about the other region? So the region number 3, when z between 2d and 3d. Now in this case, what do we have? What we have is v at z equal to, I have to integrate from 0 to z, right? E whatever dz, which is now this E, of course, I went through 3 regions. So I've got 0 to D, E3 dz plus D to 2D, E2 dz plus 2D to Z, right? Z between 2D and 3D, E1 dz. So what I end up with is, the first one is E3 times D plus E2 times D, right? Plus E1 Z minus 2D. That's it. That's my vortex in that region. Any questions? So there's no, we're just applying and understanding where the reference are. Any question at all? Is that clear? Okay, now suppose suppose that I want to so now the question is, what's the third question? So what are the capacitor on the first 2 part, right, of the layer? So now the question, any question of this? So next question will be, so the third part of the question is, I may have this plate here, have another plate over here, and have another plate over here, right? So the question is that, so this epsilon1, epsilon2, epsilon3 right here, the material, what is the capacitance C associated with this structure? I don't ask you to solve for the whole thing. So I'm asking you what's the structure for this whole thing, right? Now, this for this particular part, so let's call this C of T, the top, right? C of T basically is defined as whatever charge that is held by this Q, right, divided by the potential, the V between these two, right? The V, let's call this V, VT, right? So C over VT will be our capacitance. So what's the Q? Well, the Q we know earlier, right? Earlier from our first boundary conditions over here. So what's the charge? The charge up on the first one. Earlier we know that the Q is equal to the surface charge times the area, right? We know the area. Area is given. What is rho of S? Rho of S we solved earlier, right? Rho of S is nothing but E1 times epsilon1 is rho of S, right? Equal to rho of S, correct? We know E1 already. We know epsilon1. Therefore, we know rho S. So we know Q. And what's the potential between the two? Well, basically, we know the potential here, right? So basically, the potential between the two is VT is E1D plus E2D, correct? So what is the capacitance then? Right? What is the capacitance? In this case, it's simply, therefore, the capacitance of the top part is simply equal to rho S times A. We know what is this, which is epsilon1 E1 times the area. This area, A is the area, right? Maybe let me use a different color. This A, this is area of the plate. Okay, so now I'm back to here. C of T is equal to epsilon E1 A divided by D E1 plus E2. That's it. I don't have to memorize any formula. Any questions? Now, if you recognize it, it turns out to be, well, this is simply epsilon area divided by D, right? You have epsilon area divided by D, and then you have this product over something somewhere here. So to solve this entire problem, I don't need to know anything about special formula. I just need to know what? The boundary conditions and the idea of a potential, how does potential relate to the electric field, and that's it. And then, of course, I have to be very careful in terms of my the directions, the property of the field between boundaries, and so on. All right, let me open up if you all have any questions. I'm going to unmute every one of you. Any other questions?
Do you think you could scroll back to the last page just for a minute?
Okay. This one.
Yes.
Any other questions? So if you look at this carefully, I'm not using any fancy formula. I'm not recognizing it's parallel or serial. I know nothing about that at all. I just know boundary conditions, electric potential, and electric field. And this idea you can use to solve all kinds of problems. Any question at all on this?
Excuse me.
Yeah,
Could you plug in the values for this third voltage you found?
the third voltage. This one.
The third integral
Uh
for like E3, the distance,
huh.
E2 and E1.
Which value? What do you mean?
Could you put the values in for the different variables to see if I would like to see the voltage sum up to like the VC.
It has to, because all of this solve coming from here, right? That's our
Mhm.
conditions, right? This is here. See that? So it has to be the same, right? Because this E1 times this is E2, E1 times this is E3. Oops. Right? Does it make sense? Right?
Yep.
Because yeah. So by default, it will come back to this, right? So if you put it, the reason I don't put in number here, because they're different version of the test. So if you have your old test, you can work it out, and it should agree.
Okay.
Yeah, it continues. If you look here, it keep going, like between 0 and D, because remember our reference at 0.0, right? All the voltages when we talk about voltage over here is reference to 0. So I integrate from 0 to Z. And now what happened to my Z? If my Z is different region, then I have to, right? When my Z is in this region, for example, in region 2, right? In this region 2, then the reference is in region 3, right? So I have to sum up this whole thing plus whatever part within that region. Oh no, this is because remember inside this capacitor, where is our reference for our potential? At 0, right? That's what we put on the negative terminal of the battery. This is our reference. So all the voltage is measured from with respect to the reference. Remember when we connect the circuits, right? We connect the circuit. Let me see if I can. Okay. When we connect the circuits, we have, maybe let me draw it here. We have this, right? This is our battery. So all the voltages is with respect to this terminal, right? Right here. This is our reference. So, and then I have my capacitor here. So the voltages are, this is our reference. Or sometimes we call it the ground, right? So when I say what voltage over here, yeah, I have to integrate from all this to all the way point to whatever point we have. Does that answer your questions? Yeah. Any other questions?
You said these notes were going to be posted online, correct?
Yeah, I can save it and then email out to every. Oh no, just put it on the blackboard.
All right, thank you.
So is that to say that E1 respective to section 1 or E2 respective to section 2 is constant within that region?
Yes.
E1 no matter between 2D and 3D everywhere in that region it's
Electric
E1.
field is constant. The electric field is constant. Electric field.
Right, and therefore the voltage is also going to be constant
Oh no,
in
the
that
voltage
region.
no, the
In that
voltage is
region.
changing. No, the voltage keep
Oh,
changing.
I'm sorry. Yeah, the voltage changes with distance. That's correct. I'm sorry.
Yes.
I see that. Okay. is that physically, is that truly the case that
Yes.
E1 is exactly the same everywhere?
Yeah, it's pretty close. Now, remember we talked about that, right? You have these two plates. The boundary condition dictate that the E field has to be normal to both. And if it's not too far away, the E field will be staying the same, right? The same line. So it will be constant throughout. However, if I make the two plates are so far apart, then yeah, then it will be changing because the field will be spreading out, right? There's a fringe effect and so on. But
Okay.
within the two plate, yes.
But since this is so close, it's going to be.
Yeah, pretty constant because the boundary condition dictate it must be normal. It must be the number has to be related to the charge because the charge on the plate is constant, right? Mhm. Another question on this one? So again, if you look at here, it mathematically is pretty straightforward, but the understanding of the okay, what do you mean by potential? What is field? Are these quantities relate to each other? That's the key thing. So the critical thing here is the boundary conditions and the understanding of the field and distance. You have that potential, and whenever we talk about potential, you need to know where are the reference. Any question on this? Now, formula-wise, they're very straightforward, very easy, right? But the concept is the one that you guys need to nail it down. So in this case, I can have all kinds of configuration. I may have a capacitor that have, I may have capacitor that have a weird I may have something this. Of course, it's more complicated to solve. I can have some other material right in between, like this, for example. It's a different material floating there, and I have another material sandwich, right? I can have different material here, and so I can have put one more conductor here, but no conductor on this side. I can do all kinds of things. So I have epsilon1 here, epsilon2 here, epsilon3 here, and then I have conductor over here, right? And then I may have different material over here, epsilon4, so and so on. So if you understand the boundary condition, you can solve this problem easily. Any questions?
Yeah, just a quick refresher on that that middle conducting plate. So the charge is going to be neutral, right?
Well, because we don't purposely introduce any chart, right? Suppose initially, so let me remove this. Initially, we have, let's say here's a conductor, right? I put a plate in there, right here, right? And I put another plate. Now, initially, I don't put anything, so I put a voltage here. What happened? So I do not introduce any charge to the middle one, right? I do not put anything there. So what would happen is that this potential will force the charges, negative one, to come down here, right? Basically, I should do it this way. The negative will be coming down here, right? Because you force it, the battery forced that, and then the positive will be up here, right? All right. So now because I have this, now I create, this is it's conductor because you have free moving charge carrier, right? So what happened? The charge carrier, even though the surface is very thin, we can imagine that maybe it's slightly thicker. We can imagine this way. So a surface have two, I mean, a piece of material have two surfaces, right? So what happens is that the positive one will attract the negative charges here. The negative will attract the positive charges there. But the total charge on this middle plate is what? Exactly cancel out. That's zero. Except that it's being separated out.
Yeah, so that charge separation on that plate wouldn't really come into any effect when
Yeah, what happens is that the field, see, because negative, the field have to go in, right? Have to move in these directions. Whereas it's positive, the field have to move out, right? And because the surface charge on over here, let's call it surface at the top, and here's surface at the bottom, so T, RST, bottom, the amount is the same, right? The only difference is the sign. Now the sign will take care of it by recognizing the sign, the direction of the E field, right? Therefore, then we can actually ignore this completely. Then therefore, suppose this is epsilon2, this is epsilon3. So basically epsilon2, E2, if we call this E2, then it's equal to epsilon3, E3. We can just ignore them completely because they're the same charge right here. but we need to keep track of the directions properly, right? Any other question about this?
Yeah. So would you expect us to like do like a coax capacitor or anything that requires two or more variables of like dimension?
Well, if you have more time, I probably can ask that kind of questions. But if you don't understand this, those are moot point, right? But once you understand this, yeah, then you have a little bit more trickier now. Then, right, what happened is this: your area is different, right? So you have to it's a lot more involved now. So you have to look at the Q, and then what is the area, the charge density, because again, you have to have the same different charge density, right? That's why it's going. Suppose I put positive charges here. If I connect this to positive, outside to negative, then the field will be a radial component, right? So because the density, that give you these directions. The charge density is different. The total charge is the same, but the density is different, right? So the field over here is, oops, the field over here, let me use it. At this interface will be slightly weaker than the field over here, because here you're spread out in a wider area. Here you're spread out in a smaller area, right?
Oh, yeah, we can't see that. Sorry.
Oops, yeah, right. Because this is a smaller area, this is a larger area, right? And so the surface density is different because here's a larger area, smaller area, but the total charge is the same. So the field itself is being spread out. So at the end over here, the field is weaker, here is stronger. So a function of R, right? It's function of R in this case. The function of your diameter there. Does that make sense? Hmm. So this is the case where the field is not constant. It's actually changing with the distance further out. The further out you go is weaker because it's being spread out, right? Being spread out rather than this is not spreading out over here. Any other questions? So so that's test number, let's see. I can still keep this page. So that's that test problem. So let me talk a little bit about this. I have not, so maybe I just briefly talk about this. Can you read this or no?
Yeah, we can.
You can read that? For some reason, the screen on my computer, everything's upside down. Kind of weird. All right. But anyway, so this is test number 3, problem 2. You're given a wire carrying direct current of 4 amps is formed into a circular loop, right? And some of you missed this completely, and you try to find actually one of the example problem in the book. And then you place on an XY plane in a non-magnetic medium. Non-magnetic medium means that the mu is equal to mu 0. That's what usually people means when they say it's non-magnetic medium. So with the center of the loop at the origin, flowing in the feed direction, the current flow in the feed direction. So if I sketch this, what does it look like? So this is test number 3. Oops, let me use a different color. Problem 2, right? So in this case, what I have is the following. Again, coordinate systems. Here's my Z. Here's my X. Here's my Y, right? So my XY plane is this. And then what I have is a loop, a current loop going around like this, right? And the direction of the current, so this is the phi head directions, okay? So the current I on this loop is, so I can write the current I is equal to phi head, how many amp? 4 amps, right? 4, so this amp in the unit is amp, right? So that's what that current is. Or maybe instead of putting the 4 there, let me just put it more general. So let's call this I0. The current I is equal to phi head I0, let's say, right? So this is the vector is going around. So what's the field? Well, I asked you to find the field at this location. So I can draw it this way. I can draw it in terms of XY plane, right? So I'm interested in this problem basically asks you, what is the field expression B and H at the center of the loop? Meaning that on the XY plane, the Z is equal to 0. So in that case, if I draw it, I can draw like maybe X and Y. So I have essentially a circle, right? So I make a loop on the XY plane. The current is flowing in these directions. So this is Y. So this is I vector. Okay. Can you see that? And I ask you what's the field over in this point. So how do we solve this problem? Well, I think I mentioned this in class when we go through this example. I mentioned to you that the simplest solution only exists when at the middle or on the z-axis here. Anything outside is going to be very complicated, right? So then to solve this problem, so you're asked to figure out what's the field at this location. What's the field here, right? H at this location, H and B at this location, at the origin, right? That's what's being asked. So what are the formulation you can use to solve this problem? So basically, if I tell you the current, the shape of the current, can you tell me what's the field? That's basically the questions, right? And the direct solution to this is what we call the Biot-Savart law. Still remember those things? So let me write down the Biot-Savart law. So what's the Biot-Savart law? The differential element of the H, tiny little element due to a tiny little source is given by I, dl cross with the observation directions divided by 4 pi r square, where, now this you have to be very careful. R is equal to the magnitude of r hat, I'm sorry, and r hat, which is the unit vector, is equal to r divided by this magnitude, right? Which is equal to r divided by r, right? Any questions? So what it says is basically this. So what are the R? What does it mean? What does all this means? So suppose I have a wire flowing through this, current flowing through this wire. The amount of current is I, right? Okay, the amount of current is I here. So suppose I observe, here's my observation. I pick a observation here. So I want to know, suppose I have this tiny little element, differential element here, dl, right? It's a vector, right? This differential element dl. So then what this wire is carrying a current, and the differential element of the current, IDL, is right here, right? Times I. IDL is here, right? Is a vector. So how much contribution of this to the field? Well, if I observe it here, then this is my R. Okay. So my D of H over here, at this location, due to this current element here, here's the R. So I can solve, if I know this, I can find D of H by this relation up here. Everybody see that? So that's the whole idea. Okay. So to solve that problem number, for test number 3, problem number 2, this is what you need to know. Okay. Any question up to this point? So now, if I want to solve for this scenario, so basically, if I have a current, let me use a different color now. Maybe what's better color? Maybe the green color. All right. So suppose I have this current element right here. Oh, not good. Maybe darker drink. Maybe I have red already. Let me do orange. All right. Suppose I have this current element right here, right? I dl, right? Any questions? So what is dl? dl is nothing but, if I know that this, so the direction here, here's my r, right? Correct? So here's my r. I know that the length. So d of l is nothing but I r phi d phi, right? And phi hat. Sorry. No. I'm moving too fast. Oops. Let me do this. D of L is nothing but um, R. Oops. I keep making mistakes. It's a phi hat R d phi. Now that's dl. Yes. This differential length vector direction is phi hat. The length is r d phi, the differential element of phi, right? R is given because R is basically the radius of the whatever loop that you have, right? Any questions? So this produces a differential element. It produces the correspondingly, it produces the over here dh, right? This element produce dh. How does it produce dh? Well, IDL, and then you have this cross with the r here divided by 4 pi r squared. Everything is given. So I can find the contribution of this little element to this. Now the current is going through the entire line, right? So what is the total contribution? I simply sum up every one of them across this circle. Does it make sense? So basically, everybody follow that? So now I'm going to do is so here's the Biot-Savart law. IDL is this, right? And then what I have to do next is simply part A, magnetic field at the origin. What do we mean by origin? In other words, x equal to 0, y equal to 0, and z equal to 0, right? That's what we mean at the origin, right? So in that case, my h, so I want to find a total contribution. So what I have to do is simply sum up all the d of h, right? So basically I sum up for the entire pathway, the circle contribution to d of h, right? I just sum them up, right? Contribution for all the different elements in the pathway, which is equal to integration over that path. D of h is nothing but I dl cross with the r hat, right? Now there are different variations of the format. Be very careful. This is a unit vector, and then divided by 4 pi r square, right? This is not this is a magnitude. Okay. If we work this out, I is given. I is a constant, right? It's a DC current. dl. So this r is constant is given, right? It's a fixed radius. So I have I over 4 pi r square, and then I have what is d of l? df is nothing but, so I have to integrate the phi now because I want to express it in terms of phi. I integrate over the path. So let me write this down first. dl cross with r hat, right? So r hat is nothing but, in terms of cylindrical coordinate, this is nothing but negative for cylindrical coordinate, right? Negative r hat. This one is nothing but phi hat times r phi hat times r d phi, right? Correct. So this is a cylindrical coordinate. R hat is actually the opposite, right? So let me redraw it. For cylindrical coordinate on xy plane, so now we have this, right? This is, oops. So let me use a different color. This is, maybe, let me do this, use this, yeah. This is R vector, right? So cylindrical coordinate, so let me use a different color. Cylindrical coordinate, this is R hat, right? This is phi hat. Everybody follow that? So now, negative R cross phi, what do we get? So if I put it down here now, so because now if you look at the integration, the path over C, so you integrate actually over phi, right? D phi. So what we have here now is this is equal to I over 4 pi r squared. Now, because integral over phi becomes from 0 to 2 pi for the whole thing, and I have phi hat cross with minus r. So phi cross with minus r, which give us z hat, right? Because phi cross with minus r, phi cross with minus r give you z hat, right? So we end up with z hat. So this phi cross, and then I'll have r d phi, right? R is a constant. So basically, I end up with z hat I over 4 pi r squared. And then times r, because it's not depending on the integration, and then integrate from 0 to 2 pi d phi. R and this cancel out. So I end up with, what is this integral? This integral give you 2 pi, right? So I end up with 2 pi, cancel with 2 pi, I end up with z hat I, oops. Let me just, yeah, z hat I over 2r. That's it. That's your h. This equal to h at the origin. H at the origin. So in other words, this h at vector at 0, 0, 0 equal to this. Let me erase this. Let me rewrite it nicer. So basically what we have is h field at 0, 0, 0 equal to this. Any questions? So at a center point. How about the B? The magnetic field at 0, 0, 0. Well, the B is simply B at location 0, 0, 0 at the origin is equal to nothing but the medium has what? Is in air, right? Non-magnetic medium. Therefore, non-magnetic, therefore it's mu 0 h at 0, 0, 0. So you end up with basically z hat. Again, all of these are vector. So z hat is unit vector in z directions. I have mu 0 I over 2r. This is only at the center. Any question up to this point? Any questions? So I only see a video of some of you, not all everybody. So I now know that for a large number of group, no, we cannot show all the video. Any question about this at all? Now actually the second part and the third part of the problem, actually I was thinking about giving it as a lot of credit for those, because if you remember what we talked about in class, right? Then if you write something down that way, we cannot solve it, you get credit already. So let's see what happened here. Any question up to this point? So that's it. So this is what you get at the center of the loop. However, if you cannot even set up the problem properly, then you cannot solve it, right? So this is exactly the example problem and the formula given in the book, except the book solve for the entire axis for z at the center of the loop. This is just a 1 point in the center of the loop, right? Any questions? So now the next question is, you're asked to determine the self-inductance. So what is a self-inductance? Self-inductance is how much flux that the circuit or the geometry capture over the current. So self-inductance, so something we use L11, generally is equal to this capital lambda 1 basically produced by current 1 divided by current in the circuits 1, right? The first circuit. So in other words, now this may have multiple turn. This is essentially n times phi due to 1 divided by I1, right? So in other words, if I have multiple turn, then this is like this. However, if for one turn, this is equal to phi 1 over I1, right? For one turn. Right, for our problem, we only have one turn. So what is phi 1? Phi 1 is the flux generated by current 1, which is equal to we integrate over the surface area, B vector due to 1, right? Which is function of, in this case, X or Y or whatever. So let me not, so it's function of whatever this, right? Dot with ds, right? So if we use the cylindrical coordinate, so for example, for this case, if we use this coordinate system, if we use cylindrical coordinate system, right? So then at any point, I have this r and this phi, right? Correct. So in this case, at any location here, so this is it b1 function of whatever r value and phi. And d of s, then you have dot of, what is d of s? D of s is then is a unit surface, which is dot with r, whatever r distance is, and then
Sorry
the
to interrupt. Can you please move it up again,
you're
please?
gonna say, oh, sorry. So let me erase. So what is d of s in this case? The d of s for the spherical, I mean for cylindrical coordinate system for this kind of surface here is the normal surface normal is z hat, right? And then you have the r d phi, the r d phi, right? So the differential element, if I blow up here, basically look like this, right? Can you see them? This is dr. This is r d phi, right? So this then the surface is normal. So this is the b1. This is d of s. Remember, you have to put a dot product because this is a vector. This is a vector. Okay. So you can see that this is very complicated integral. Why is it complicated integral? Because this b is function of position, right? So let me show this. Any question up to this point? So the challenge is solving this. And as a matter of fact, to solve this, the b at a different location, somebody in NASA actually write a paper how to solve this. So intuitively, any question up to this point? So I have to, in order to solve these, I have to determine what's the magnetic flux density at every location inside this circle, right? Inside on the area, correct? Any questions? In the first part, we only solve the B at this location. We only solve it at this location for part A, right? Now, in order to solve the second part of the questions, I need to know all the B at every location inside this area. Everybody follow that? Now, that's a tough problem. Why is it a tough problem? Well, let me show you. So the problem now, let me make it big. We have something like this. This is our Y. This is our X. Right? And then we have a circle like this, assuming it's perfect circle. So I know how to solve for the B at this location. This is known, right? You solve it for part A. So this is B, 0, 0, 0, right? What we want to solve is, we assume that at Z equal to 0. So we want to solve for other locations. So maybe here, at this location, B at some X, I'm sorry, let me use a spherical, cylindrical coordinate. So maybe here, let me use a different color. What would be a good color? Maybe a green one. Okay. So I have here, this is my R, this is my phi, right? If I use the cylindrical coordinate on the XY plane, then I end up with, this is, the Z of course is 0. So I have R phi 0, right? So in other words, for on this XY plane, I don't have to worry about the third element. I just have to worry about R and phi. So it's function of R and phi only. We know how to solve this. This is not a problem. But to solve for this point, what happened? If I want to solve for the magnetic field, let's pick a point. Let's pick suppose now I want to solve at this location right here, right? The field at this location is contributed by this element by this element, by this element, right? By this element and so on. Do you see that? So at one point, the contribution coming from all of this. So the equation is quite complicated. I can bring a paper, the solution to you all. Somebody solve it. Actually, solve much more general. But you know something, that within this area, the maximum value is this. As you go out, it gets weaker and weaker, right? So the strongest magnetic field here, the weakest magnetic field there. That's what you should know. So how do you solve that problem? How do you solve this? Well, one way is to just approximate. You say, well, it's some constant multiplied with this, right? And you assume it's constant value. So what I'm looking for in this particular problem is whether you remember this. Do you remember this one? And then you remember the definition of self-inductance and mutual inductance. So self-inductance, the flux is produced by the same current, and you divide it by the current. That's self-inductance, right? And then if you mention something about you may have to make approximation and you know how to put it in there, then you get a full score for this. I just want you to see whether you get the idea, right? So I thought it was a giveaway problem. Any questions? So now, do you understand this part? Every point at every location, the field is contributed by different element all the way, right? And this is what makes it complicated. So what I can do, I think I can put a copy of the paper developed, and then we can talk about that when we have next review session, for example. Any question about this? So I think we can talk more about this once I give back the paper, which is this Thursday. And so far, how do you think about this system? Is it okay, or maybe those that have issue, concern that you cannot see? Any comment?
Like in Zoom?
Can Zoom?
No, like using the program.
Yeah, the Zoom. Yeah, using this platform. Is it okay, or is it? Should we go back to the classroom, or?
This is wonderful.
This works great.
Yeah, also okay. Yeah, let me know if you think that this is kind of difficult. But once you get used to it, I never done like this because in the past we are talking only. We have the meeting agenda, so we just talk. Here I have to sketch and drive. So it looks like this is a good work, right? With a camera system and this system, I think you don't need to see me, right? You can see my hand, right? But I can see some of you, but some of you turn off the camera. Is that right? Any comment about this? So if not, then we can do this on Thursday afternoon. Well, if I'm not on campus, or we can pick other time. So if a group of you want to have a discussion, we can do this. Just let me know so I can set up the meeting.
Yeah, somebody made a good point in the group chat. So this is more convenient than waiting at school. So I agree with that. It probably helps people's schedules and stuff.
Oh, there's a group chat in here. Let me check. Where is it? Gee, is this within Zoom? Is that right? Is it the chat is within the Zoom, or? How can I am the monitor for all of this. How can I cannot see it?
It's the bottom toolbar for me, right next to share.
Oh, right next to share. Oh, I only have manage participant. I can manage you
Try
guys.
Alt H. Try pressing Alt H.
Oh, I'm using the Mac, so let me see. Oh, chat. Okay. I can see the chat. Good. I can see the chat. All right. Good. Then okay. So XD. What is XD? Anybody?
Cross product of the.
Huh? You guys
Dude.
kind of trick me. Huh? Cross product now. You have.
So I
Okay.
just saw like a laughing face, like his eyes are.
Okay. So the XOXO, right? Kind of thing, right? Okay. Good. Oh, I can. Actually, this is good. Then you guys notice that you can just type, say, I want to talk. Then you can mute, everybody else can see that. It's a good idea, right? So this works well with for everybody. Then we can do this, and this good in a sense that we don't have to find a room. That's a nice thing about this. It took us several days to just find a room. In terms of the sound quality and the video is okay.
Yes, it's pretty good.
All right. Yeah. All right. So I think it's almost 7 o'clock, and some of you have to go to the senior design. Oh no, different class. So we will continue discussion this two problem. this one and the other, the mutual inductance, maybe on, let's see, we can set up a Thursday session. Let me check my schedule, or if needed, we can also do tomorrow. If you, so why don't we do this? A group of you, why don't you coordinate among yourselves? Say, okay, these are the time that works for most of us. I don't expect everybody can come, right?
I think this is the time that works best for everybody, or most of everybody.
Okay, so Tuesday, so we only have a few more days left, so we can do this on Thursday again if needed, right? So let's plan on doing all this again on Thursday. Let me check my calendar. I'll confirm with everybody. Once it's working out, I'll email it to everyone, just like what we did last time.
Sounds good.
Before I start, any question at all? So let me type here. It works. Good. So yeah, so we can use this instead of raising your hand, or because if you turn on your microphone, then it's gonna be very noisy. So video is okay, because video I can see who is talking, or who is you can type message, and then after you type in the message, nobody respond, then you can turn on your mic. All right.
Dr. Tjuata, I had one quick question.
Mm-hmm.
For
funny. You look funny. Is that you got a wrong camera or what?
no, is this my face? Oh no, it's my face. I'm in the room, the IEEE room.
Okay.
So for the third problem in that exam, you asked us to do the cylindrical coordinate. Is it okay that if we do the XYZ coordinate instead of the cylindrical coordinate?
That's why it take me so long to create a paper. Yeah, I try to give you the benefit of the doubt. If you use a cylinder coordinate, it's simpler. But yes, you can use XYZ if you're careful. Yeah, you can do that.
Okay, perfect. Yeah, I just had that quick question. Thank you.
Any other questions? Anybody else? Looks like what? Tuan Ni, or is that what's your name? You have a gaming chair? That's nice.
Oh yeah.
Okay, at least you get your gaming machine to good use then.
Yep.
Any other comment, questions, concern? All right, so yeah, you can also shoot me. So if you guys want to organize and say, well, let's do something on Saturday morning. If my schedule is available, we can do that. That's what the beauty of this system is. It's much more flexible. Okay, so if no other questions, then see you all in class on Thursday morning then, right? I'm gonna assign homework maybe sometime from chapter 7 and 8 sometime tomorrow, maybe late this evening or tomorrow. Okay.
Thanks, Dr. Tjuata.
Good night, everyone.
Yes, sir. Thank you.
See you all. Bye bye.